Hello, this episode is all about isolation transformers and variacs, how they work, what they are good for, and also how I'm currently building two separate variable output voltage isolation transformer units with additional lab power supply capabilities. Furthermore, this episode can help you to learn something about the power grid in different countries, secondary side switching in switched mode power supplies, and even about a 1950s transmitter that will play a role in this video. This episode is meant to answer the following questions. First, what is an isolation transformer unit good for? Second, why is electric isolation a safety measure? Third, how is such a unit typically built internally? Fourth, how did I design and construct the units I'm working on at the moment? And fifth, how can an isolation transformer unit be upgraded to a DC lab power supply? Okay, so let's try to answer question 1. What is such a unit even good for? An isolation transformer unit with a variable output voltage can be used as a safety measure for experimenting on offline switched mode power supplies and also for repair jobs. It can be used for powering 115 volt devices from a 230 volt line. Also for testing old devices like tube radios by slowly stepping up the supply voltage, as well as for testing of 50 and 60 Hz transformers. And furthermore, it can serve as a base for a DC power supply with high output voltages and currents. So, okay, but just listing these different points might not yet be enough to convince you. And that's why I will now step by step explain to you why and how these are valid points. For that, I will now start with a simple experiment, and I will then try to give you a broader understanding of the issues at hand by talking about the power grid, earthing techniques, transformers, and much more. This is a neon lamp type mains tester in the form of a screwdriver. When you connect it to the contacts in an electric outlet while putting your finger on the metal piece on top of the screwdriver, and it happens so that the tester has contact to face, a little neon lamp inside the tester will light up, as can be seen here. When you connect it to the so-called neutral, however, it doesn't light up. Now, here we have one of the isolation transformer units that I'm working on at the moment. The lower of the two outlets delivers 230 volts AC, just as before. But when I connect the tester to either of the two electrodes, no light can be seen. So, to answer the questions why this tester can be used to determine which of the mains conductors is a phase, and why it doesn't light up when connected to the isolation transformer unit's output, is key to understanding what this video is all about. And that's why I want to talk about what the power grid beyond the electric outlet in your home looks like, and figured it's time to get a little overview. Please notice that the graphics which I'm about to show you depict the power grid in my home country of Germany, which might vary from the one in your respective countries. But I will say more about that as we go along. Despite recent changes like the advent of renewable energy and of high voltage direct current transmission lines, the power grid still largely remains a three-phase AC system with a hierarchical structure, with the major sources of energy at the top, the industrial consumers in the middle, and the households at the bottom. At the highest level, we have the 400 kilovolt grid that is supplied with electric power from the most powerful power plants in the country. The synchronous generators inside most power plants, however, only deliver a supply voltage between 6 and 30 kilovolts. Therefore, so-called generator transformers have to step up the supply voltage to the 400 kilovolt level. In Germany, these are the nuclear power plants and so-called brown coal or lignite power plants. This situation may vary in other countries, since Germany has been the world's #1 producer of lignite for many decades, only recently rivaled by Indonesia. Here you see a photograph of the Garzweiler lignite surface mine near Grevenbroich, Germany, where the world's largest bucket wheel excavators are used to mine for this resource, mainly used for electricity production. In the course of the Fukushima Daiichi nuclear disaster, the government has decided to shut down all German nuclear power plants, a policy that seemingly no other major industrial power seems to follow. The 400 kilovolt grid is then coupled to the 230 kilovolt grid, which is mainly fed by mid-sized power plants. In the case of Germany, these are, for example, hydroelectric power plants and black coal plants. This again will be different in such countries as China, Brazil, the US and other nations which operate large-scale hydroelectric power plants which far exceed the power level of the mid-sized power plants I'm talking about. Some of them even utilize high-voltage direct current transmission, operating at voltages even higher than 400 kV. The 230 kV grid is then coupled to the 110 kV grid, which is connected to large-scale industrial operations. These factories are fed from the 110 kV grid, but might also supply it from small industrial power plants which might produce electrical energy exceeding the needs of the factory. The 400 and 230 kV levels are sometimes referred to as extra high voltage, while the 110 kV level is called high voltage. Coupled to the high voltage grid, you find the so-called medium voltage grid with voltages somewhere between 1 and 50 kV, with 10 and 20 kV being typical values. Other than the high voltage and the extra high voltage grids, the medium voltage lines are not used for power transmission over big distances, but for regional distribution. Connected to the medium voltage grid are so-called distribution transformers, which supply the households with 400 volt three-phase AC in what is called the local low-voltage grid. One distribution transformer may supply a street or even a small village with electric power, but in some cases single households which are situated at remote places may have their own distribution transformer. The same is true for local small-scale industry, administration and schools, which also in many cases have a distribution transformer of their own. A more recent development, but ever more important in Germany, are local wind farms and solar power plants. These are also coupled to the regional medium voltage grid. So, why do we have so many different voltage levels on the power grid? Well, high and extra high voltages allow the transport of large amounts of energy over large distances at acceptable efficiency and with conductors of comparatively small conductive cross-section areas. On the other hand, these voltages require a lot of safety measures and are much too dangerous for households. The different voltage layers are all a trade-off between cost efficiency, required power handling capability and safety. The system was further built around AC rather than DC, mainly because AC can be stepped up and down by simple 50 Hz transformers. To step DC up and down, you require switching converters, which were invented much later and which require modern semiconductor devices like thyristors and IGBTs. I live in a rural area without any large-scale power plants. We have no extra high voltage transmission lines around here, but you often see 110 kV lines like the one on this picture. The 110 kV line is going to the local substation where the regional medium voltage grid is connected to it. Right here you can see both a high voltage and a medium voltage line next to each other. Right here, you see a distribution transformer mounted on a pole. The three phases of the medium voltage grid can be seen up in the air, while the 400 volt line is implemented as an underground cable right here. And here you see yet another medium voltage line and another distribution transformer which feeds some local houses. These distribution transformers are particularly interesting for us, because they are directly involved in answering the questions we had about the little neon tester. And to understand how and why, let's follow the way of the current from this point to my electrical outlet. The local distribution transformer's primary side is connected to the medium voltage grid. The primary windings are often connected in a delta configuration, while the line is not carrying a neutral conductor at all. The transformer then steps the voltage down to the 400 volt level, with the secondary windings connected in a star point configuration. The star point is then connected to the earth near the transformer, constituting what is called Betriebserde, for which I chose the English translation system ground. From here, the three phases and a fourth conductor, called Protective Earth Neutral Conductor, abbreviated PEN, leads into the single households, where it is then split into the so-called neutral N and the protective earth conductor PE. This is just one variant of several possible earthing systems that is used in Germany and around Europe. It's called the TNCS system, which is short for the French words Terre neutre combinée séparée, Earth neutral combined separate, meaning that the star point is earthed, that Earth and neutral are combined and then separated inside the house. The three phases are then leading via several fuses through the electric meter, through the residual current device, and via the circuit breakers to the various single-phase and three-phase loads. Small and medium loads, which require a supply voltage of 230 volts AC, are connected between one phase and neutral, while large loads like this three-phase induction motor are connected to all three phases, while no neutral connection is necessary, as long as the load burdens the three phases symmetrically. All metal enclosures and surfaces, not linked to the phases, are then connected to the protective earth, which needs to be earthed inside or near the house once again. This is done with a ground electrode. Furthermore, via the so-called equipotential bus bar, the metal parts of the central heating system, metal plumbing and other metal surfaces around the house are connected to it. This pretty much completes the electric wiring found in your average household. As far as I know, and that is from books alone, three-phase AC is not standard in households in North America. Instead, a system called split-phase power is used in many places. It derived from the Edison DC system and is, except from some rural regions in the UK, completely unheard of in Europe. It is quite different from the German system. First of all, the medium voltage grid is usually realized in a star point configuration rather than in a delta. My guess would be that this is done because the distribution transformers are not three-phase transformers at all, but are connected with a single primary winding between two phases of the medium voltage grid, representing an unsymmetrical load. I'm not even sure though if American or Canadian medium voltage grids carry a neutral conductor or not. I'm sure some of my American viewers will know the answer, and I would like to know more about that system. Any American or Canadian experts out there? Please leave a comment below. Since this is not a polyphase transformer, it of course does not have an earthed star point at the secondary side, but instead it has an earthed center tab, which, like the star point in Germany, makes the supply voltage for the household earth referenced, allowing the use of an RCD. But I will not say anything about the internal wiring because I have not found any reliable sources about that. I again would call for my American and Canadian viewers to write something about that in the comment section. Despite all details, however, the general usefulness of isolation transformers should be given in that system as well. So let's return to the three-phase system and the European household. Now we have all we need to explain how the mains tester works, which safety measures are existent here, and what an isolation transformer would change. The only thing missing is a human being, here represented by the so-called resistance model of the human body. This model depicts the human body as a system of resistors, roughly representing a worst-case scenario, meaning that the resistance of a human body would normally be higher. Starting from these values, which I found in an electrician's training book, you can calculate a resistance of 975 ohms from one hand to both feet when the legs are seen as in parallel connection. Now let's see what kind of safety mechanisms are existent in this system. First of all, we have a range of fuses on the way from the transformer secondary to the load. These fuses can also be modern circuit breakers, but the physical principle behind their operation is not so much of interest right now. More interesting is in which way they act as safety measures. Fuses melt when their rated current is exceeded for a certain period of time. That condition can be caused by a very low load impedance, or in the most extreme case, by a short circuit, where at least two conductors are in direct contact. If there was, for example, a short circuit between one of the phases and the neutral right here, this fuse would blow, separating the circuit and preventing overheating and possible fire in the transformer or the line. If two phases would be in direct contact, either one or even two fuses would blow. In an ideal world, both would blow, but it might occur that one fuse is simply a little bit faster than the other one. After the conductors have entered the house, a set of fuses follow. If here a short circuit would occur, it would be these fuses rather than the earlier fuses that would blow. That is because there is a hierarchy of descending rated currents in these systems. In this way, a fault condition and a subsequent shutdown of a part of the grid stays as local and limited as possible. The same is true for all possible subsequent fuses and circuit breakers. So this is basically the first safety measure, preventing overheating and fire by recognizing overload and especially short circuit conditions. But do these fuses protect you as a human being from electrical shock? To answer this question, let us first get an overview over what electrical currents do to the human body. For that purpose, let us take a look at this chart. There are 4 general current ranges between which we will differentiate and explore the effects on the human organism. At a current of 2 milliamperes flowing through a part of your body, you will feel a tingling sensation. By itself, that is not yet dangerous, but a negative consequence often is that this sensation will frighten you, making an uncontrolled movement which possibly could harm you or others around you. At a value of around 10 milliamps, muscle paralysis can set in, preventing you from releasing your grip or other ways of disconnecting the electric circuit you are unwillingly a part of. At a current of 25 milliamperes, muscle spasms and elevated blood pressure occur, leading to respiratory paralysis, which means that you can no longer breathe. From now on, you are in danger of death. This completes the first range. In the circuit range from 25 to 80 milliamperes, several terrible effects can occur, again having very negative consequences. Stomach cramps and a feeling of nausea, strong muscle spasm that can possibly lead to bone fractures, and worst of all, a state called ventricular fibrillation can occur. What is that? Well, your heart muscle receives electric impulses which make it contract periodically in order to pump blood through your body. This normally occurs somewhere between 1 and 3 times per second, but when a 50 or 60 Hz alternating current of sufficient strength is flowing through your body, it will virtually send 100 or even 120 pulses per second through your heart, disturbing its natural rhythm. This will lead to the collapse of the circulatory system and after a couple of minutes, brain death. In the third range, between 80 milliamps and 1 ampere, this effect will set in after just 0.1 seconds of exposure. In the final range, above 5 amperes eventually, your body would be severely burned, what often leads to death after several days or weeks. Ventricular fibrillation, however, will most probably not occur. So, as you can see, lethal currents are far lower than even the smallest fuses that are normally used in your house installation. Even if you were directly connected from one phase to another, would the circuit breakers not react? Because of the comparatively high resistance of your body. With the theoretical value of 975 ohms, for example, only 410 milliamperes would flow through your body if you were connected from phase to phase, while the average circuit breaker is rated for 16 amperes. To better understand this, let's take a look at this picture. Let's say a human was to have contact to one of the phases out here directly. The current would flow from the distribution transformer secondary through the overhead line into his body and through the legs to the earth, where it would flow through the ground to the ground electrode, from there via the PE conductor and over the combined PEN conductor back to the transformer secondary. In this case, the fact that the star point is connected to Earth becomes a curse to the poor guy because it closes the electric circuit via the ground he is standing on. The same thing would happen if he had touched the line here or here. The current ratings of all these fuses are all much too high to help him out. But that's of course where the residual current device or RCD comes into play. First of all, what does the RCD do? For that, let us connect a single phase load like this light bulb between one of the phases and the neutral. The RCD is now measuring the overall sum of the currents through all 3 phases and the neutral conductor. Since all current that passes through the light bulb is returned over the neutral and through the RCD, the overall sum of the current is 0 amperes. Therefore, the RCD will do nothing. Now a symmetrical three-phase load is connected. Again, all currents enter the load via the RCD and are returned through it again. The sum of the currents is again 0 amperes. But if we now connect a load between one of the phases and the protective earth, the current that returns to the distribution transformer does not pass through the RCD, but uses the PE as a return path. If the current sum is now higher than what the RCD is rated for, it will open all its switches and disconnect the load from the grid. Nowadays, these RCDs are normally rated for 30 milliamperes. With that figure and the supply voltage of 230 volts, you can calculate that the resistance required to activate the RCD is around 7.6 kiloohms. For a person standing on the ground, that would be the sum of its body resistance plus the total resistance of the earth return path to the ground electrode or to the system ground respectively. This shows you that a ground with very high insulating capabilities will actually disable the RCD from reacting, while on the other hand it might limit a possible body current from being dangerous to you at all. The absolute time that an RCD should take to react are 0.2 seconds, but in most cases modern RCDs are much faster. The idea basically is that the RCD will disconnect you from the grid should you happen to touch one of the phases, as you can see here. This should ideally happen so fast that ventricular fibrillation cannot occur. But since we have seen that currents below 30 milliamperes can already be deadly, you should be cautious never to touch the phases directly anyways. But not always can you know if a part is under voltage or not. A typical fault would be this case, where one of the phases of a motor has contact to its metal enclosure. If it wasn't earthed and you would touch the motor's enclosure, it would be as if you hung directly on the phase. For that reason, all uninsulated metal enclosures and parts are normally connected to the green and yellow protective earth conductor. In that way, the RCD would disconnect the motor from the grid, and if high currents are flowing, the circuit breakers might even blow. With this knowledge, we basically know everything we need to explain how the neon lamp mains tester from the beginning of the video works. If you touch the metal part on the top of the tester screwdriver and apply it to one of the phases, an electric circuit is closed via your body. The current flows from the distribution transformer through all the fuses and the RCD, through a current limiting resistor and through the neon lamp, lighting it up. Then the current returns via your body and the ground and over PE and PEN to the transformer. The RCD doesn't react. The current sum is not 0 amperes, but it is very small and well under 30 milliamperes and even well under 1 milliampere, not being dangerous for an adult person. If you apply the tester to the neutral on the other hand, both sides of the tester are basically connected to earth ground, which means that there should ideally be no potential difference between its two electrodes. Therefore, no noteworthy current flows through the lamp and it doesn't light up at all. If now an isolation transformer is connected between one phase and neutral and the neon tester is applied to either one of the ends of its secondary winding, no current is flowing because no closed electric circuit exists. Should the lamp light up nonetheless, even though there is no measurable resistive path to earth ground, the reason is the capacitive coupling between the windings and earth. While that capacity might be high enough to light the lamp, no dangerously high currents will flow, even if you touch one of the secondary ends directly. That's basically the main advantage of an isolated system in comparison to an earth reference system with RCD. In some working environments and situations, this and other secondary advantages of the isolation transformer are the reason why it is recommended or even mandatory for some applications. Never must you come in contact with both ends of the secondary at the same time though. The current will flow through your body and in this case basically directly through your heart. Don't forget the old saying, always keep one hand in your pocket. This saying is generally a good advice when working on power lines and offline equipment, but in this case it's more true than ever, because the RCD will not react no matter what you do on the secondary side of an isolation transformer. So, okay, this was a lot of theory, but I hope you found it interesting nonetheless. What remains for me to do now is basically to show some examples for using an isolation transformer unit, and of course to talk about the units I'm working on at the moment. And to answer the open questions which I mentioned at the beginning of this video. All that more practical stuff will be done in part 2, which will go online in the coming days. I'm working on it, and see you soon.